key step is share the desktop. And, okay, could everyone see this clearly? Do I need to increase the font? Is everyone okay? Okay, thanks. And oh, by the way, we actually have been allocated some physical offices for TA office hours, but our TA came to the office yesterday, but still was locked. I don't know, maybe it still have something to do with the construction. I will need to double check with the front desk and to make sure it is working properly. So I think to be convenient, like to not let you guys to wait outside or be locked outside, we're gonna still use the Zoom link for the office hours this week, but it should be ready for the next week. Okay. Yeah. So today we're gonna first wrap up the cost policy and cost web page, all those kind of stuff, and I think last week we talked about the letter grid mapping. You can see the standard here. Someone asked, okay, if there is more higher expectation for the grad students or lower expectation for undergrad students, I would say we're always talking about the same piece of content. All the topics are the same. In most of the cases, the the homework assignments tasks are the same. The only difference is that if we, as undergrad students, you might be easier to get higher grade like A than the grad students, because you have because the grad students will have a higher bar. But other than that, there's little difference. And also, we talk about the late policy. There's some kind of late penalties. As long as you do some late submissions, there will be 10% late penalty, and then every 24 hours we'll incur another 10% of credit, but we do not receive late submissions, I mean, more than 48 hours. So that's why I kind of like repeat again, I really suggest you to start doing homework early, especially for homeworks that require some programming assignments, because you do need some time to debug your algorithm, test them on the given data sets to show reasonable results. If you don't allocate enough time, very probably it won't work. Okay. And homework submission, we mentioned that we all accept homeworks written with LaTeX. We believe this is very important and it's very fundamental because, I mean, no matter which particular science or technology area you're working on, when you wrap up some report or papers, whatever, they will be written as LaTeX. And also because when you need to deal with a lot of like mathematical formulas, using LaTeX is always the best choice rather than using Word. And here we give some sample text file for you to, if you never have heard of it or never use it, you can start with a simple example. And also we will share the LaTeX source we use to composite our homework assignments. You can just reuse that and write down your solutions on top of that. It will be very convenient. And also I highly recommend using this online LaTeX editor, Overleaf. It's free unless you want some like more professional functions, but it's basically it's free. And you can just simply, I mean, upload the LaTeX source file we released in the Canvas and start working on that. It is like you edit, you immediately see what you can get. So it's very, very convenient. But if you insist on using your own LaTeX editor, it's up to you. But this is just a very convenient choice. And attending final exam, here is just some policy, like if you're unable to take the final exam at scheduled time because of some like emergency or something like something like that, please contact the instructor head, and we might be able to schedule another time for you. And you missed final exam due to some issues like 911 or emergent illness or something like that. So please notify us within 3 days of exam and provide some kind of document. We need to collect document just for fairness to be, I mean, we want to be fair to all the students, right? It's not we distrust you or something like that. We just want to be fair. So once we have got your notification and also document, we can consider scheduling a makeup exam, but don't miss it. And after 1 month, 2 months, come to tell us that, okay, you missed this final exam because blah, 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 because at that time, the final grade has already been uploaded to the registrar office. It's very hard to revise it. Okay. Academic policy. There are some kind of policy guidelines. I believe everyone knows that, so I'm not going to repeat them. But just to emphasize that no cheating, no plagiarism, and if someone is caught cheating on the homework and the test, they will receive a failing grade for the course. And for the collaboration, right? So I'm not saying like you are not allowed to discuss with each other when you do this homework assignments. You are encouraged to do so. But when you write down your solutions or coding those algorithms, you should do it by yourself. Right? You cannot just copy and paste others' code or others' written text, right? And it is fine that you guys discuss offline, like how can we prove this theorem? How can we calculate that entropy, information gain, all kinds of stuff. Is feel free to do so, but just don't paste the detailed steps on Canvas because we encourage you to discuss with each other rather than you just throw out all your stuffs into another one. If you collaborated with another student and you have some kind of like worrying that, okay, the answers, even you guys wrote them down like by yourselves, right? That might still kind of like resembles much. It might cause kind of like unnecessary suspicion. You can explain that in your homework submission. Like, okay, I have discussed about this with my fellow friend in this class. His name is blah blah blah, and we kind of we have agreement on how to solve that problem. So don't misunderstand. We don't cheat. We don't copy with each other. That's one. Otherwise, if we found okay, it's so similar and it looks like more plagiarism, you will get point deducted. But of course, if you this grading is not fair, it's not the truth, you can come to us and give some explanation. That's within our policy that you can request regrading and also give some explanation. But if you request regrading, please do send me an email first and highlight the reason you want the regrade, and then I will forward your request to TM. This is or TA. This is just to be formal and to be fair. Okay, any questions so far? Okay, and finally, if someone is physically challenging in any aspect, don't hesitate, don't be shy, just let me know, and ask for what kind of help you do need. We can definitely talk to the administration or even facility office to offer the help. Okay, so this is just a briefly wrap up syllabus of this course and then introduce the policies, and hopefully this will give you some kind of more comprehensive view and also what we expect you to do so. As I emphasized previously, we do want you to feel you do learn something from this course, so not feel like extremely painful, right? So that's why we spend quite much time in discussing every detail in the course policy, grading policy, project requirement, and so on. So and all those information is not only covered in syllabus. Of course, you can refer to you can look at the syllabus if you want, but probably the most convenient choice would be just to go through this course website. Right? As I mentioned before, you can access my homepage and then click into this course link in the teaching section. You enter the course website, or there's some link in the Canvas. You can click into that as well. And all the schedule information, grading, and project information are listed here. And here there's an information tab. It gives a list of prerequisites and course policies, and also reference books. And not only in the books written in the syllabus, we provide more external resource links for your reference. Like if you want to quickly look up linear algebra. Right, there are a bunch of very good references for linear algebra, and most of them are free online. And also, if you want to review the concepts and probability and statistics, here are a few very good references for you to quickly catch up. And here, topics, I think we have discussed in our syllabus. I think other than those tabs, the most important tab will be the lecture section. Someone asked me, like, what if they cannot join the class in person? Will we have some lecture video? And the answer is yes. And we not only have this lecture video, we also stream it online, meaning that right now, if you stay in your apartment, you can still watch the video online. But unfortunately, we cannot like interact with you through Zoom online. But here you can see that before every lecture, let me enlarge the font. Before every lecture, we're gonna release the lecture slides, and you will have access of that. And also when we do the lecture, we stream that to the YouTube channel. And after that, we're gonna release the link of the YouTube. So now that means later, if you want to review the lecture video, you can go back to this link and watch them. Okay. And also we have some assignment notice here, and we have some due. Of course, we're gonna make an announcement on Canvas. Okay. So far, any question regarding the course web page, settings, and the syllabus? Okay, if everyone is good, everyone feels good, we'll continue with our lecture, continue with our topic. Okay, let me, okay, this is, okay, this is where we are, where we were last time. Again, this link also gives my homepage and also the course website. And again, I want to emphasize this course is focused more on fundamental aspects and ideas about machine learning rather than some specific area like deep learning. If you're interested in deep learning, consider Professor Tom Henderson's certificate program. And again, we do want you to learn efficiently and don't put too much time on that, although you do need some commit enough efforts on that. But how do you efficiently learn that? We do want you to take classes to learn the models and algorithm. If possible, it will always best to join the class in person so that you can interact with me directly rather than just watch the video, right? And then finish homework assignments in time to deepen your understanding. That means once we release homework assignments, please start doing that early, at least 1 week before that, right? If you do it like 3 hours before deadline or only at the end day, it's very possible that you cannot make it or your submission will be imperfect, right? So take advantage of our office hours and try to finish it as early as possible and implement those algorithm models by yourself and doing course project for using machine learning techniques to solve problems. This will definitely deepen your understanding about how you can apply machine learning in practice, right? And on Canvas, feel free to post questions and discuss, and feel free, and our TM will watch the Canvas question, and they have some allotted time period to watch those Canvas questions and answer you as soon as possible. But I will request you to post your questions on weekdays rather than weekends, because on weekends the TAs, their response might not be as fast as you want, right? Because they have some schedule on the weekends, so they will definitely respond to you, but most probably will be on the following Monday. So if you have some questions, you want to get a very quick response, most wisely, it will be just posted on weekdays so that you can get answers very quickly. And again, workload, I want to emphasize again, 6 homework assignments. Homework 0 has been released and due on this Friday. And the other 5 homeworks, most of them will include both written problems and programming problems. And regard course project, you need to report several reports like midterm, like proposal, like final report, and you need to do a lot of programming and also practice of using machine learning to address those problems, and you need to take a final exam. So overall, I have to say that workload is pretty heavy and might be challenging for some of you. So again, I don't want any of you like feel being tortured throughout this class, right? If you do feel okay, this is too difficult, and make me irritated, make me pissed off or frustrated, and you might not be you might not be like sufficiently prepared for this class. That's totally fine, right? You can consider taking some like prerequisite course, like especially 3190 Foundation of Data Science course taught by my colleague. They will give you a much better preparation rather than being struggled in this class. I don't want anyone to struggle here. I want you to feel, okay, I do learn something. I feel like confident to continue onto machine learning study or machine learning practice in the future. That's our expectation, rather than making you feel like feel bad, very bad, feel frustrated at the end of this semester. Okay, before we start talk about basic knowledge review and decision trees, our first machine learning algorithm. Any question regarding the course settings, workload, or any other concern? Oh, looks like everyone is comfortable and confident. Okay, great, thanks. Appreciate that. Appreciate your patience for this, for me to go through this tedious stuff. Okay, so we're gonna first give a quick review of those basic knowledge. If you already started doing homework 0, you might review those by yourself. But again, I'm to be able to help everybody, right? We still want to give you quickly review to refresh your mind. And I do believe most of you have heard of those concepts and have been familiar with those stuff. So, okay. So we're going to first introduce the concept of random events and probabilities, right? So this is a basic concepts in statistics. So because the real world, the practical world is filled with uncertainty, right? So we do want some kind of mathematical framework for us to quantify and measure the uncertainty of all kinds of events, right? If we believe that events, the occurrence of that event has associated with some randomness, like I don't know if today is gonna rain or not, right? I don't know I'm gonna be a millionaire in 10 years or not, right? I do want some kind of rigorous way to calculate those kind of uncertainty or reason about those reason under this uncertainty, right? So that motivates the development of probability theory and statistics, right? So the most the fundamental concept comes from how do we use a math term to define events, right? So we usually use sets to represent events with randomness, right? So each element in that set can be viewed as kind of atomic outcome, right? Like if the experiment, if the things are interested in is to toss a coin, right? Suppose one event is that you can toss a coin for 5 times, and I'm interested to know that which tosses give you heads up and which tosses give you tails up, right? So then we can represent our event as a set of 5 elements, right? Each element is either has a head or tail. So we can represent even A, 3H and 2T means that, okay, 3 heads and 2 tails, and B, like 3 tails and 2 heads, right? So once we have such kind of mathematical representation of events, we can assign a probability to measure the chance that event happens, right? So we assign a probability over A means that I'm going to assign a number between 0 and 1, right? So indicates the chance that this particular event A happens, and this particular chance of event B happens, right? And given those set representations, we can use set operations to composite more complicated events, right? Like if I take union of both sets, like A union B, what kind of event does it represent? Yeah, I heard that, right? Both A and B happen, right? What if we take, sorry, it's not union, intersection. Sorry. It's my fault. Yeah, it's intersection, right? What if I take the union of A and B? A happens or B happens, right? There's some kind of subtle difference between the two, so don't get confused here. So they're different. Like A and B happens. Like let us take one specific example. Like one event will be, okay, today is gonna be gonna have some rain, right? It's gonna have some rain, and the other is that today is gonna have some strong wind. Like for example, the speed is over 45 miles per hour, like, and these are 2 events, right? So if we take the intersection of A and B, it means that, okay, we're gonna have an event that both we have a strong wind over 45 miles per hour and rain, right? However, if we take the union, what does it mean? Yeah, it can be like, as long as raining happen, it shows A union B happen, or B happens, it shows union B. If A and B both happen, it also shows A union B happens. Right? So you can see if A covers a larger range of things that gonna be happening, right? So that's why when we measure the probability of A union B, it's usually bigger than the probability of A intersection B, right? Because it tells that A happen or B happen, right? A includes the event that A happened but B not happen, A not happen but B happen, and A and B both happen. So it's just one subset. A union B is just one subset of A intersection with B is just a subset of A union B. Okay? Any question? Everyone's comfortable? Okay, and then we have this fundamental probability definition, right? So we measure the probability of A union B is equal to P of A plus P of B subtracted by P of A intersection with B, right? This is a basic a formula of computing the probability, but this can be explained using the so-called Venn diagram of the event representation, right? So if you let me use a pen, right? So you can draw one circle represent event A, right? And another circle represent event B, right? So P of A union B is actually measure the area A union B, right? So when you compute that, it is equal to compute P of A, which is just this part of area A covers, and subtract it plus P of B, the other area B covers, but you add the overlap twice, right? So you need to subtract the overlap. This overlap is actually the probability that A and B both happen. So we do have some general version, like suppose you have a n events, A1, A2 to AN, right? How do you compute the probability of A1 union A2 union A3 until union AN, right? There's a one long formula is actually kind of alternatingly as I'm subtracting those unions and intersections, right? So I'm not gonna list the full formula here, but it is listing in almost all the statistical book or Wikipedia. If you're interested, you can take a look at them. Okay, so after we introduce the random events, right? We'll talk about the random variables. Random variables, why people define random variables? But very roughly speaking, you can view, okay, I'm gonna map some practical things which I believe is random into some numbers, right? Into real numbers, into discrete numbers, integers, whatever, or complex numbers, and then I can roughly think that, okay, those numbers, their choices have associated with some kind of uncertainty. So now all the probabilities, chances are quantified by looking at the value of those random variables, right? So why people do that? It's just because we want some kind of more consistent and abstractive framework that can be used for every discipline, right? That's why we first do some mapping operation, like we only consider some abstract numbers in numerical space or real space, complex space, to and then we want to find out some patterns or theorems or lemmas to characterize the relationships. And once when we apply it to some practical applications, now we only build up such kind of mapping, we can address that problem. Right? And here is one example, right? So if we want to use random variables to describe or model our experiment of tossing a coin, right? We can introduce a binary random variable x, right? X is 1, meaning that your outcome is a head, right? When variable is 0, meaning that your outcome is a tail. Now, if we toss a coin for 5 times, right? We have 5 random variables, right? X1 to X5. Each random variable records in the corresponding toss whether you have observed a head or tail, right? So now we want to if we want to describe some particular event, like we have less than 3 heads, right? We can use this inequality to represent this event, right? Rather than introducing some set. Remember, we just use this set to represent one event, right? So, but now we can use some mathematical inequality or equality to describe an event, namely the summation of all x1 to x5 is less than 3, right? And then if we want to quantify the probability or chance of that event, we just compute the probability of this inequality holds. But more rigorously speaking, random variable should be viewed as a mapping, a function, rather than some numbers. It is mapping from a probability space to some real space, and also you have to specify some structure on that two spaces, like sigma algebra, those kind of stuff. But we're not. But this we will not cover that because it's more like probability theory. We mainly give some quick review of random variables. You only need to know. You only need to have a sense that, okay, when we talk about random variables, you can view like, oh, okay, the value of those numbers, the choice of values of those numbers is associated with some probability, associated with some uncertainty. That should be enough. Okay, so now given the definition of the events, random events, and random variable, we can define the so-called joint probability and the conditional probability, right? So suppose we have two events. The joint probability of A and B just means the probability A intersection with B. And so don't be confused here. It's not probability of A union with B. It's probability of A and B both happens. Both happen. Okay. So we can decompose this joint probability as a marginal probability P of A times a conditional probability, that is, given A happens, the probability B happens. Right? And it also can be decomposed in a symmetric form. It is equal to P of B times P of A given B. They are the same. And the same form applies to the joint probability over random variables. So P of the joint probability of two random variables, X and Y, can be decomposed as P of X, which is marginal probability, times the conditional probability P of Y given X. And also symmetrically, P of Y, marginal probability, times the conditional probability of X given Y. Okay, this is the basic formula. Everyone is comfortable, right? And then a very important concept is called independence. Okay? So what does independent mean? So intuitively speaking, it just means, okay, the chance that A and B, the two events, both happen, or the chance of A happen has nothing to do with the chance of B happen. Right? So if we want to express this in a more quantitative way, it's just saying like the joint probability of A and B is equal to the product of the marginal probability of A and marginal probability of B. So basically, you can view A and B happen independently. So the chance they both happen is just the product of the chance each individual happens. Okay. And similarly, we can define independent random variables if the joint probability of independent variables X and Y equals to the product of their marginal probability. Marginal probabilities, that means X and Y are independent to each other or mutually independent. Okay. So third, if we contrast to the original definition about the joint probability and the definition of independence, we actually can have another definition of independence. Right? So if we compare the joint probability of A and B here, right, and the joint probability of two independent events A and B here, right, we can conclude that if A and B are independent, that basically means the conditional probability P of A given B is the marginal probability P of A. Right? This is actually even more intuitive. Right? So the conditional probability measures that, okay, conditional on the fact that B happened, what's the how likely A will happen, right? And it turns out to be the same as A happened without knowing B happens or not. Right? So it actually reflects the fact that A happens or not has nothing to do with B happens or not. Right? So this is another way to define the independence. Right? And similarly, if two random variables are independent with each other, we can also check that by looking at if the conditional probability of the random variable is the same as the marginal probability of the random variable. Any questions so far? Everyone's comfortable? Okay, so here just for simplicity, I just ignore a little bit difference here. Like if X and Y are continuous random variables or discrete random variables, so the P here are kind of like a uniform representation of them. But here I just want to emphasize a little bit to avoid any misunderstanding of concept, right? If X and Y are continuous random variables, and the P here is usually referred to as a probability density. Okay, the density function, right? And if X and Y are discrete random variables, and here it just means probability functions. Right? But regarding the definition of density functions and cumulative density functions, all kind of stuff, I will rely you to review them. Right? This is just the basic definition. Okay, so we can generalize those joint probability independence to the case where we condition on some third random variables, right? So, for example, condition on third random variable, a random even C, we call A and B are independent if their joint probability condition on C is equal to the product of their own conditional probability condition on C, P of A given C times P of B given C, right? So the same as the joint probability, except that on both sides of this equality, you need to condition on a third random variable. And similarly, the conditional independence of two random variables, X and Y, implies that the joint conditional probability given C is equal to the marginal conditional probability of X given Z, and multiplying with the marginal conditional probability Y given Z. Right? The only difference is that you are conditional on third random variable Z. What if what? Well, if they're not independent, well, you cannot decompose them into this product. You need to model them or calculate them jointly. That's it. Because actually, one key modeling component, I mean, the probabilistic learning is to find out or assume some kind of independence or conditional independence to simplify the structure. Otherwise, you have to write down the joint probability, right? It will be very complicated. Other question? Okay, now given the joint probability, the definite joint probability, we can compute the expectation and variance, those important statistics, right? So the expectation of a random variable is defined as an integral. Of course, when X is a discrete random variable, you can just replace the integral by the summation, but they're basically in those definitions are interchangeable, right? So it is integral of X multiplying the probability X takes that value, right, across its domain. Right? You do the expectation, you do this integral, you get this expectation, right? So basically, you can view as kind of like weighted average of the values your random variable can take, right, in the domain. Right? And we can then generalize the definition to a function of random variable. Like suppose you have some function of X, like X squared, X cubic, sine of X, right? You want to take expectation. How can you do that? It's relatively straightforward. You just inside this integral, you just replace X with G of X. Then you do this integral with respect to P of X, the probability density of X. Then that's how you compute the expectation of G of X. Okay. And then another very important statistic is called variance, right? So variance is defined as the expectation of the square of the random variable subtracted by the square of the expectation. Right? But conceptually, it just means, okay, how far away on average you are moving from the expectation, right? And of course, a variance means that you need to also take a square of that. But basically, expectation means variance indicates that, okay, how far away, because random variable, it can take all kinds of values, right? I want to know, okay, how wild and how far away it can jump away from its mean, right? And the smaller variance means that, okay, this random variable is less random. It's more like to show up surrounding the mean, right? If it is a variance very large, means this random variable is really, really random. I mean, so okay, it can jump very, very far away from the mean, right? So you can view like it's kind of like stableness of this random variable. So, and then we'll talk about what if X is vector, right? So when X is scalar or when X is number, you can compute the variance in this way, right? And when X is vector, then when we talk about variance, it's usually referred to the covariance matrix. Like X if X is a like 10-dimensional vector. So we're not only interested in, on average, each element of X, the variance, right? How it jumps away, how far it can jump away from its mean, but also want to know the correlation between X1, X2, X1, X3, X2, and X3, all those kind of stuff. And those stuff together forms the so-called covariance matrix, right? Like suppose X is 10-dimensional, then covariance matrix will be time by time, right? So the computation of this covariance matrix conceptually is the same as the definition in the scalar case. You take expectation of X transpose subtracted by expectation of X times expectation transpose. So here I want to emphasize this guy is a matrix. Why? I mean, why this is the matrix? Yeah, right. Don't forget our linear algebra, right? S is vector, right? And the common vector multiply is transpose, which is essentially an autoproduct, right? Autoproduct vector is a matrix. So similarly, the expectation of X itself is also a vector, and then multiplied by its transpose, which is a row vector, it will give you another matrix, right? You subtract this matrix by EX transpose, you get covariance matrix, and the covariance matrix is known to be always positive semi-definite. And also, based on the conditional probability, you can define a conditional expectation and a conditional variance, right? So how can you compute conditional expectation? Yes, exactly, right? Just look at here, right? The conditional expectation is that, okay, you're gonna replace the marginal probability of X by the conditional probability of X given Y, right? And similarly, when you compute the variance, a conditional variance, look at here, right? When you take expectation, you just replace P of X by the P of X given Y. Right? That's how you compute the conditional expectation, conditional variance. Right? But here I want to emphasize a tiny or subtle stuff, right? So how should we view the conditional expectation? Is conditional expectation some kind of a constant number, like 0.3 or 0.4? I heard no. Anyone can explain why? Yes, I heard that, right? Let me repeat what you said, right? So we cannot simply view the conditional expectation as some kind of knowing constant number. Why? Because it relies on Y, right? When Y takes value 0.1, it might give you a number 0.4, right? When Y takes 0.4, it might take a second number 0.2, right? So basically, we should view that this conditional expectation of a function of Y, right? Because it depends on Y. In this integral, in the expectation, you have marginalized all possible choices of X, but Y is still conditional there. So they essentially are a function of Y. And Y is a random variable. That means they're random variables as well. So there's one problem in our homework assignment 0. Ask to check your understanding about conditional expectation and conditional variance. Hopefully you won't get confused about that. Okay. Okay, now let's jump to another important definition. It's called convex function. Right? So convex function is defined as so-called domain is called convex region or convex set. So what does convex set mean? Right? So basically, I mean, geometrically or intuitively, you can view like convex region as some kind of shape of domain which is all outward in everywhere. You don't have some like inward curves or shapes. But more rigorously speaking, if we pick up any 2 points in this convex region or convex set, you can draw a line, right? You can draw a segment, right, which connect X and Y. We demand that all the points which connect on the line which connect X and Y must stay inside this region. Then it's called convex set. If any point on this segment is outside region, then it's not a convex set. For example, this kidney-like domain. Right? So when we pick up 2 points x, y, and we draw a line segment, right? Draw a segment connects x, y, but for this right part, all the points on this right part is outside of the domain. So this shape is not a convex set. So this is just definition. Like, don't ask me why. It's just definition of convex set, convex region, right? So then we can define a so-called convex function, right? Defined on the input domain are defined on a convex set. So if function f is convex, that means the following inequality holds for arbitrary inputs chosen from the domain. Right? For example, if I choose arbitrary 2 distinct inputs x1 and x2, and choose an arbitrary number between 0 and 1, then we have this inequality holds. That is, if we first take a linear combination of x1 and x2 in terms of this t, right? T is between 0 and 1, right? And then evaluate at this combination of the input, this function value will be no bigger than you just evaluate x1 and x2 with the function f, then take the linear combination according to t. So you can see that on both sides, they're doing same kind of linear combination according to t, right? The difference is that on the left-hand side, I'm going to first do the linear combination on the inputs, x1, x2. Then I apply the function. On the right-hand side, I first apply the function evaluation over x1, x2. And then I do the linear combination according to t. Okay? And the convex function means that, okay, the left-hand side must be always less than or equal to the right-hand side. So this inequality seems kind of like a complicated, right? But it has a very nice and intuitive explanation in geometry. Okay? So once every time if you want to memorize what's the definition of convex, you can try to draw a figure like that, and you'll get to know. You can write down this inequality very easily. Right? So here, this black curve is our instance of convex function f of x, right? So how does f of x satisfy this definition or inequality, right? So you can try to pick up any 2 inputs on this axis, x-axis, which is in the domain of f, right? x1, x2. You pick up any t, right? Between 0 and 1. That means if you do the linear combination of x1 and x2 according to t, it will be in between, right? So this is where tx1 plus 1 minus tx2 stays at, right? So now let us check the left-hand side, right? You do the linear combination of the inputs first, you get the location in between, and then you evaluate the function at this location you get here, right? This is our function value. And then what if we first evaluate the function at these 2 endpoints, x1, x2, we got here and got here, right? And then you do the linear combination with the same weight coefficient t. This is where the linear combination arrives at, right? So now you can see that the linear combination of the function values at x1, x2 is actually bigger than the function value at the linear combination of the input. Okay. That's the property of the convex function. You can pick up any 2 other points and try that. You will see that you will always find the right-hand side is above the function curve. That means it will be bigger than the left-hand side. X and t. X are any points in a domain, and t is any value between 0 and 1. There's no like specific restriction on the choices of t. You just specify the range. And the convex means that, okay, for arbitrary choices of x1, x2 in your domain, an arbitrary choice of t between 0 and 1 you should have this inequality satisfied. Then you can say this is a convex function. Otherwise, it's not a convex function. Yeah. So if you look at the right-hand side, right, this is where f of x1, right? And this is where f of x2, right, at the other end. Right now, if you want to do a linear combination, I mean, geometrically, you just draw a line, combine them, and then draw a vertical line, right? You get a cross, right? This is where your t of fx1 plus 1 minus t f of x2, right? Any other questions regarding the clarification? Okay, so here we give some more examples of convex functions. Like if your x is just single variable, exponential function is a typical convex function. Negative logarithm x is typical convex function, and actually logarithm of x is called concave function. That means if you flip the inequality, right, you make this as no less than, right, and any function satisfy this inequality for arbitrary x1, x2, and t, it is called concave function. If x is a multivariable function, right, meaning that x is a vector, there are a lot of examples of convex function as well. Like simplest case will be affine function or linear function, A transpose x plus b, or quadratic function, half x transpose x. Like, now, given the function, right, how can we determine if this function is convex or not? Right? Of course, we can show the convexity according to the definition, right? But that is really quite complicated, right? Quite hard. So we have two other commonly used criterion to determine the convexity. Right? First, if this function is differentiable, then as long as you can try that for arbitrary 2x and y in the domain, this inequality holds, then f is a convex function. And we're gonna talk about why this, right? There's some theorem like if this inequality holds, you can derive the definition inequality will always hold. And the second commonly used criterion is that we just look at Hessian matrix or second derivative. If this Hessian derivative is if this Hessian matrix is positive semi-definite, then this function is always convex. This function is convex. Right, and of course, if x is a scalar, right? X is a number, and the Hessian matrix is reduced to a number, right? That just means if the number is non-negative, then this function is convex. Okay. So for convex function, there is a very, very important inequality. It's called Jensen's inequality, which in the future, if you got a chance to do some probabilistic learning and variational inference, you see that the foundation of that is based on this so-called Jensen's inequality. So what does Jensen's inequality tells us, right? Just tells us that if x is a random variable and f is convex function, then you take the expectation of x and then evaluate f will be less than or equal to, you take the expectation of f of x. So it's like, remember x is a random variable, right? F of x will be a random variable as well. So you can take expectation of f of x as well, right? It just says, okay, the function of a random variable's expectation will be upper bounded by the expectation of random function of random variable, provided this function is convex. And it is pretty easy to show that according to the definition. So I will leave it as an exercise for you. But you can imagine that what if x is just a discrete random variable, like if you toss a coin, it has two outcomes, right? Or you roll a dice, 6 outcomes, right? So you actually have 6 possible values that x can take, and each value you have a different weight, right? This is very similar to the definition here. It's a weighted summation, right? It's a weighted summation of 2 inputs, and you apply the function, it will be less than or equal to, you apply the function first and do the weighted summation. Right? So it has the same same flavor of that. But if you want to give a rigorous proof, you need to make a little bit tweak on that. It's not hard, at least. And similarly, you can make it a little bit more complicated that you apply some additional function over x, like g of x. But remember, g of x itself is another random variable. That means if you will g of x is a random variable y, you apply this inequality again, you arrive at here. Okay. So the last piece I want to briefly mention is about matrix derivative. So we won't densely use matrix derivative throughout the semester, but it will always be good for you to get a sense of that. That is also reflected in our homework 0. There's one problem or two problems that ask you to try to derive the gradient or derivative in terms of the vector or matrix format. If you feel like it's too difficult, too hard to do that, it's fine that you view them element-wisely, and then you derive, okay, for each element, what is derivative, and you try to organize them in a matrix vector form. That's totally fine. Or you can also apply those basic rules to take the derivative over vectors and matrices directly. That would be much more convenient. Okay, so basically, the derivative on matrix or vector random variable, not random variables, matrix or vector objects is kind of similar to numbers or scalars. They also apply some kind of rules like chain rule, like exchangeable rules or commuter laws, those kind of stuff. You just follow these rules to apply them and decompose your derivatives into several terms and then add them together. And that's it. Like, for example, if you want to take a derivative over a constant matrix A is simply 0 and 0 matrix of the same size of A. If you take the derivative over a scalar alpha times a matrix variable X, it's the same as we understand. Right? For numbers, like you just move alpha outside, right? You take the derivative over this matrix X and times alpha. And similarly, like something and partial X plus partial Y equals partial X plus partial Y. I don't want to repeat that. It's really straightforward. But here, something interesting might worth your attention. Like if there's a square matrix and take trace, right? Take trace operation. What's the trace operation? Anyone recall definition of trace? Yes, exactly, right? The trace is simply the summation of the diagonal elements in a square matrix, right? So if you want to take the derivative of the trace of element, remember this is a scalar, right? And then it is equivalent to first take the derivative over the matrix variable X and then take the trace, right? And similarly, this is called element-wise product, and also is a Kronecker product. And this is like if you want to take a derivative of the inverse of X. Here we assume that X is invertible, right? And then the X is a square matrix. This derivative is equal to minus X inverse, and take a derivative of X and X inverse. So you can view like this is a matrix. It's just kind of like matrix version of the chain rule for the inverse function, right? And as to why this like it has such kind of form, I don't know. This is kind of like arranged and derived by some smart people like 3 decades ago or 4 decades ago. Like, there's some good reference. You can take a look at all those formulas. You don't need to really derive this or prove that. You just use them as some kind of dictionary, apply them, and combine them, and you get a result. And here is one online book. It's called Matrix Cookbook. I think it's released by University of Toronto. It is free online. It contains almost all the commonly used matrix derivative conclusions. That means in most cases, you really don't need to derive those matrix derivatives vector derivatives from scratch. You just mechanically apply those results and then combine them together. Okay. Any questions so far? Okay, great. We still we have 5 minutes left. I'm gonna quickly go through our supervised learning topic. I'm gonna quickly go. We're gonna give a quick start on that. So now we're gonna start our machine learning, right? Our major topic now is this long trip, right? It's long trip. So as we discussed before, right? We're gonna first introduce or the major theme of this course is the supervised learning, right? So before we talk about every specific supervised learning algorithm, we're gonna first give a framework or general setting of supervised learning, right? You see that all those algorithms are inside this one big framework, and then we're gonna talk about several important concepts and ingredients in conduct the supervised learning, and then we're gonna start with the so-called decision tree. Okay? So first, what is supervised learning? Again, we don't want to give a very abstract definition from the beginning, right? We want to start with some detailed example. Right? Suppose we are assigned a task to classify some news articles, right? Those news articles might come from New York Times, might from Washington Post, or whatever, web blogs, whatever, right? So every time we're going to give an instance of news article, right? You know, it's just a paragraph of text, probably including some figures, numbers, and so on, right? And once we're given such an instance, we're going to tag this instance with some label, right? Maybe this piece of article is talking about sports, right? And we might have a bunch of other labels like politics, like entertainment, legal things, like you know, divorce case about Johnny Depp and his ex-wife, like those kind of stuff, right? It might be entertainment, might be both entertainment and the legal stuff. So you got a bunch of labels, right? So if we will this task, right? Consider you got a machine, right? You do this continuously, right? We're essentially trying to map every possible news article into one or several of labels in some given set of labels, right? Like one piece of article might be sports, the other might be business, the third be politics and entertainment and all kinds of stuff, right? So naturally, we're going to define two sets of things which are important in our supervised learning task. One is called instance space. Right? The other is called label space. So instance space, as the name suggests, includes all possible news article we want to tag, right? And label space includes all possible labels we can use to label. And more abstractly, right? To conduct any machine learning task, not only in supervised learning, right? We need to first define what is your instance space, right? Namely, the set of examples you want to give some prediction. Either you want to label it, either you want to predict some continuous value, like stock price, like my bonus, right, at the end of this year, right? This is called instance space, right? And then we also need to define the so-called label space, namely the set of all possible labels we can use to predict. Like if you're doing like spam filtering, then you might have only two labels, right? This piece of email is spam or not spam, right? If you're making prediction about precipitation amount, right, you might give some continuous range about the possible labels. And once you identify the instance space and label space, you actually have a formulate your task. Right? And now the learning amounts to finding out a mapping from the instance space to the label space. Right? You map every possible instance in the instance space to a possible label in the label space. Right? So from what we have learned, right, from our primary school, we know that it's best to represent this mapping as a function, right? So we believe that there is an underlying ground truth of this function gives the labels for every instance in the instance space. Then the goal of learning, of machine learning, essentially is to find out this target function. Or more realistically speaking, to find out some close or satisfactory approximation to this function. Because in many cases, you'll see that you'll never be able to find out the ground truth function. So that means learning is a searching procedure over functions, right? You definitely have like numerous possible candidates of this function, right? And you want to find out a smart way, efficient way to identify this function, or at least get close to that target function. Right? And when we conduct the learning, we never assume that, okay, we know the exact form of function. We can only view examples generated by this function. For example, okay, you got a bunch of instances, sample from the instance space, you got their labels given by the ground truth or target function. Right? Now, we want to use those input instances, examples and their labels to search over the target function. Right? So this is called supervised learning. So basically, we're gonna prepare or collect a set of labeled training data, which you can in general view as pairs, right? Every instance of the training data is a pair of the instance and label of that instance given by the target function. Then once we have collect this data, we give them to our learning algorithm. Now we can just assume it's a black box. Right? And learning algorithm will search over this target function guided by this training data, okay? And in a finite amount of time, and then it's gonna return you some learn function G, which is also mapping from X to Y, right? From the instance space to the label space. Okay? Then this whole procedure is called supervised learning. So a natural question will be, okay, can you consider of other protocols, right? A very naive change will be, okay, why not we just remove all the labels? I just sample a bunch of instances. Can you learn this mapping? If you're doing this, it's called unsupervised learning. And further, if you mix your data, like partly are labeled instances, part are unlabeled instances, it's called semi-supervised learning. So you can see that learning protocol is only dependent on how you're going to prepare the data. Okay, let's stop here today and see you on Thursday. We're going to continue with the supervised learning framework and decision tree.